G'day, let's continue this Equilibria unit. Looking today at buffer solutions. We're going to describe how buffer solutions regulate pH, calculate buffer solution pH, and then we'll investigate some applications. So to start off with straight away, let's jump in to a solution as its name might suggest. We use the word buffer in our everyday vocabulary to describe similar things. A pH buffer is a solution that minimizes changes in pH upon small additions of an acid or a base. So adding an acid or base to water will readily change the pH. Let's talk about why this is. What have we been saying pH is? Well, pH is a measure of hydrogen ion concentration on a logarithmic scale, where if we're adding acid, essentially what we're doing is we're increasing that hydrogen ion concentration, and then through this calculation, that will subsequently decrease pH, that acidic region being less than 7 on the pH scale. If we're adding a base, an alkali, what we're doing is we're adding or generating hydroxide ions. And we can think of hydroxide ions as removing hydrogen ions, in this equation that we've looked at a few times. If we're adding hydroxide ions, we're essentially decreasing the hydrogen ion concentration. And on our pH calculation, that's going to increase the pH above 7 up to 14 being that basic region on our pH scale. So what are our buffer solutions doing? Well, they've got to remove hydrogen ions or remove hydroxide ions to keep the pH within the constant region that it's trying to achieve. Importantly, however, they do only work within a certain threshold. No buffer solution can cope with an excess of acid or base. Obviously, if you add a huge amount, the buffer can only buffer so much of it. So very large amounts of acid or base are invariably going to change the pH. We have two types of buffer solutions that we're going to look at. We're going to look at acidic and basic buffer solutions. They work in slightly different ways. So we'll look at these in depth. But look, let's think about what an acidic buffer solution is going to be doing. Well, it's going to buffer the solution within the acidic region. So if we want to keep the pH within a acidic threshold, a pH less than 7, whatever that may be, for whatever purpose, we can use an acidic buffer solution with a pH less than 7, which is often made from a weak acid. So I've got my weak acid designated here, A for acid, showing that proton it's able to donate. The Bronston-Lowry definition, acids as proton donors. It's a weak acid, so we've got the system at equilibrium here. And the salt of its conjugate base. If we think back to the conjugate pairs, we have the acid and then we have the conjugate base over here. So it's a mixture of those two things. Whereas the basic buffer solutions, on the other hand, they're going to be working within that basic region of the pH scale. So we're going to have a pH greater than 7, often made from a weak base. So I've got B for base there, able to accept a proton. It might be a neutral base, might be an ionic base with a negative charge. I've just shown the lone pair of electrons there. That's able to accept a proton from the salt of its conjugate acid. So if we think of this base as being water soluble, it's able to accept the hydrogen from water, and we generate those hydroxide ions. Those hydroxide ions very much able to affect the pH through that further reaction with the hydrogen ion as I just showed. So look, we got to work through both of these. So let's begin with the acidic buffer solutions. Let's consider this by considering a typical example. So we need a weak acid, so we can use ethanoic acid and the salt of its conjugate base. Well, let's look at the weak acid equation first of all. So we've got the ethanoic acid and we got the conjugate base. So we need a mixture of both the weak acid and a salt of its conjugate base. So let's use something like sodium ethanoate, that being the conjugate base there. We get the salt of its conjugate base. Importantly, the conjugate base salt is going to fully ionize into sodium ions and then our ethanoate ions more accurately. So what have we done? Sodium ethanoate has added lots of ethanoate ions, increasing the concentration of our ethanoate ions because we've added them because it's fully dissociated. So let's consider what this is going to do to this equilibrium over here. If we're adding the ethanoate ions, we're increasing the concentration over here. Le Chatelier's principle, all that good stuff we've been talking about in this equilibrium, that's going to push that equilibrium very much back to the left-hand side. And we're going to further favor the backwards solution over here. So what our solution ends up containing from the mixture of these two things is a bunch of reserve supplies that are going to be integral for how it buffers the solution. So we have reserve supplies, a very high concentration, or a relatively high concentration, maybe more accurately, of the unionized weak acid. So we have a high concentration of that species there. We have reserve supplies, a relatively high concentration of our conjugate base over here from that salt that we've added. So we've got relatively high supplies of both of these. And then we have sufficient hydrogen ions to make it an acidic solution, because again, if it's an acidic buffer solution, it's trying to maintain the pH in the acidic region. So what we can do is our sodium ions and our water can be ignored, and we can simplify the buffer just as this equation up here. We can change the region of pH that the buffer solution operates it within. So the pH that the buffer solution regulates can be changed by different types of acids and their corresponding salt for the conjugate base, or by varying the ratio of the acid to the salt. By increasing, having more acid than salt or more salt than acid, we can change what pH region it is buffering. We'll look at some of these calculations a bit later on. But let's just think conceptually about what is occurring to keep the pH constant in these situations. So crucially, we have a relatively high concentration of our weak acid, a relatively high concentration of our conjugate base, and the hydrogen ion sufficient for whatever pH region we're trying to buffer. So let's think what would happen if we added acid to this solution. Well, acid is increasing the amount of hydrogen ion concentration. So if we're increasing the hydrogen ion concentration to keep the pH constant, we would need to remove the hydrogen ions that are added to return it to the pH that it was originally at. So that's what our buffer's doing here. Let's think in terms of Le Chatelier's principle. If we increase the concentration of hydrogen ions, the equilibrium is going to shift to the left-hand side, and it's subsequently going to decrease it and maintain that pH. But importantly, we have a very large supply of our ethanoate anion, so we have no significant change to its concentration as we add these small amounts of the acid in. We have a relatively large concentration of our weak acid as well. So relatively speaking, these concentrations remain pretty much unchanged, but what we have done is we've removed the hydrogen ions from the solution, which allows us to keep the pH constant. What about our alkali or base? What if we're adding base? What are we doing? We are increasing the amount of hydroxide ions. The hydroxide ions are able to react with the H+, and what it does is it decreases the amount of hydrogen ion concentration. So what does the solution need to do to keep the pH constant? It needs to subsequently increase the concentration of the hydrogen ions again. Always talking in terms of Le Chatelier's principle. Let's think conceptually again. If we decrease the amount of hydrogen ion, the equilibrium is going to shift to the right-hand side and subsequently increase it again. So we have the hydroxide ions reacting with the H+, they remove it from the solution, the equilibrium shifts to the right and puts the hydrogen ions back into the solution. But as before, because we got the relatively large supplies, reserve supplies of both the weak acid and its conjugate base, it means there's essentially no significant change to their concentration. The pH can remain unchanged by dealing with these acids or bases that have been added. All right, let's consider our basic buffer solutions now. And we'll do that by talking about another common example. In this instance, it is the weak base and the salt of its conjugate acid. So weak base of ammonia, and let's think of ammonium chloride. Let's look at these two equations again. So ammonia is a weak base. So we have the ammonia and we put it into the water, and it's able to accept the proton from water and form the hydroxide ions. And we have its conjugate acid there. So we can have a salt of its conjugate acid that's able to fully ionize. And we're doing a very similar thing to last time. We're having all these reserve supplies of both the weak base and its conjugate acid in the solution. which is going to be integral for buffering it. Ammonium chloride adds lots of ammonium ions. So fully ionizing, we add lots of this. It pushes our weak base even further to the left, giving us lots and lots of that as well. And we have all our reserve supplies that we can summarize here. Reserve supplies, a relatively high concentration of our unionized weak base, which in this case is our ammonia. We have reserve supplies, a relatively high concentration of the conjugate acid, which are our ammonium ions. And we have sufficient hydroxide ions in the solution to keep it at the pH that we are aiming for. Again, let's simplify this. Let's ignore the chloride ions and let's simplify the buffer as our equation up there. Here's a question. Why don't you give a go at seeing if you can explain how well buffer solution minimizes the changes in pH upon additions of small amounts of acids and base. Not dissimilar to last time. Think in terms of that equilibrium position, what our reserve supplies are doing, how could that buffer our pH in the basic region. And then why a solution of aqueous ammonia alone is unable to achieve this. All right, so let's consider our ammonium chloride buffer. We have relatively high concentrations of both the weak base and its conjugate acid, and hydroxide sufficient for the basic region we want to be in. What would adding an acid to this buffer solution do? Well, if we increase hydrogen ion concentration, which is adding the acid, it's going to react with the hydroxide, and subsequently we're going to decrease the amount of hydroxide in the solution. So what the buffer needs to do is it needs to increase the amount of hydroxide ions to maintain the pH that it was at. So the OH minus ions react with the hydrogen ions and remove it from solution. Equilibrium shifts to the right hand side. We generate more hydroxide ions. pH remains constant. But again, because we have these relatively large concentrations of NH3 and NH4, there's no significant change to either concentration. They're able to keep buffering and maintain that pH if some more acid is added. What about if we added a base to this buffer solution? What would that do? Well, if we're adding a base, we're increasing the hydroxide ion concentration. So therefore we are increasing the hydroxide ion concentration, to say the same thing twice. That's going to push equilibrium to the left-hand side. So the buffer needs to remove the hydroxide ions to keep that pH constant. So there you go, increase the concentration of hydroxide, equilibrium shifts to the left. But again, same thing, we have our reserve supplies of the ammonium, of the conjugate acid, ammonia, the weak base. They remain relatively unchanged in concentration and our pH remains constant. So yeah, if we're increasing the hydroxide ions, we're driving that backward reaction. The NH4 and OH converts back to the NH3 and H2O over there. So why would the ammonia alone be insufficient? It's because we've got a weak base here. So we've got a equilibrium very much to the left-hand side already. So if we don't have any of these reserve supplies in there, then the NH4 plus is insufficient to be able to react with the OH minus. Without that, conjugate acid salt giving this high reserves, the position of equilibrium far to the left would not create enough ammonium ions to remove the addition of hydroxide, which means it wouldn't be able to buffer it. All right, let's put some numbers to this, calculating the pH of a buffer solution. If we consider buffer solutions as weak acids, we can calculate the pH with a very similar process to what we've seen before, involving our Ka values. We looked at in a previous video, which is there if you need it. So let's remind ourselves what our Ka values are telling us. Our Ka values are an equilibrium constant. So if we have a weak acid, we have an equilibrium between the acid and its conjugate base. So if we were to write an equilibrium expression for this, we need to have the products concentration over the reactants concentration. Now, if we wanted to know the pH, what we would have to do is we'd have to rearrange to get H plus as the subject, and then we can calculate that if we're given the other variables via our pH equation. But we were just saying before that in our buffer solutions, we make them by having a concentration of our weak acid there, and then having a concentration that we add of our salt as the conjugate base. So if I write this slightly differently by substituting these in, so our Ka value is equal to the H plus times by the concentration of the salt, which we know because, theoretically we've made the buffer, and we've got the concentration of the acid there. So now if I rearrange this to get the H plus as the subject, we can then plug that into our pH equation. So what does that look like rearranged? It looks like this over here. The H plus is equal to the Ka times the concentration of the acid divided by the concentration of the salt. Now, in fact, you could do this in just a single step to get the pH, because we can do a whole bunch of logarithms. We know that if pH is equal to the minus log of H plus, well, we got the H plus there, so why don't we multiply both sides by minus log, right? So that on the left-hand side becomes the pH, because pH is equal to the minus log, and we've got a value for what the minus log of the Ka is, and that is the pKa. So if we're given the pKa value, we can pop that one in there, or we can calculate the pKa from the Ka, and then some other logarithmic stuff happens to this part of the equation, and what we end up with is an equation that looks like this. So, like I say, if we multiply both sides by the minus log, because that is equal to the pH, that becomes the pH. Minus log of the Ka is the pKa, and then, like I say, some stuff happens here. They get swapped around, plus sign gets in there, but that's another equation to get the pH directly if we're given the pKa. So we can combine the two equations and simplify using logarithms to get the pH of a buffer solution. Let's practice that. I have a question here. Calculate the pH of a buffer solution. If we have that much of that much of that, and I've given you a Ka value for our acid of that. Give it a go. Two equations. Use either of them. Use both of them. Let's go through how to do it. So if I come over here and we get the question up so I can write it down. All right, so let's first of all, let's calculate the concentration of hydrogen ions if we're given a Ka times by the concentration of the acid divided by the concentration of the salt. So it's just a bit of a plug and play here, really, isn't it? What were we given? We were given a concentration, so that there is going to be our salt, that there is going to be our acid, that there's our Ka value. So our value for our acid concentration was, well, let's do our Ka first of all, 1.8 times 10 to the minus, what does that say, minus 5. And then we're going to multiply that by the concentration of the acid, which I'm trying to read was 0.2. And then divide that by the concentration of the salt, which is 0.1. Let's make sure I got that the right way around. 0.1 is the salt, 0.2 is the acid, 1.8 times 10 to the minus 5. Brilliant, plug and play. This will give us the times 10 to the minus 5 times 0.2 divided by 0.1. This will give us our hydrogen ion concentration, which is going to be 3.6 times 10. Calculator's still not giving me scientific notation. 1, 2, 3, 4, 5. It's probably because I've done nothing to change it. So that's our concentration of hydrogen ions, and we can then plug that into our pH equation minus log of our answer up there, 3.6 times 10 to the minus 5. That will give us a pH equal minus log, where's the log button of the answer? That'll give us a 4.4 pH if we give that two significant figures. Look, let's also do this other way. Let's use our other equation up here, where the pH, you can just do it in one step, is equal to the pKa plus the log of our salt concentration divided by our acid concentration. So our pKa is equal to the minus log of our Ka. Maybe I'll do it without a bracket there. Minus log of our Ka. Our Ka value was 1.8 times 10 to the minus 5. And then we're going to plus that to the log of the salt concentration. Let's make sure we get this the right way around. 0.1 was our salt, 0.2 was our acid. So it's going to be 0.1 over 0.2. And then what should happen is plug all this in and we should arrive at the same answer of 4.4. So let's do our due diligence here and make sure that's the case. -5 plus the logarithm. Oh, I pushed the wrong button. Oh no. Start again. Minus log, feel free to fast forward, times 10 to the -5 plus the logarithm of 0.1 divided by 0.2 gives us, look at that, the same answer. Cool. 4.4 is our pH. That answer makes sense because we've got an acidic buffer. We've got an acid. So pH equal to 4.4. What about if you've got a basic buffer solution? What do you need to do here? There's a few ways to consider it. The one way I'm going to talk about is to consider it from the conjugate acids perspective. So it's not too dissimilar to what we discussed above. So look, if we think about, a basic buffer solution where our base is accepting the proton to form the conjugate acid, well, let's just write it, like I say, from the conjugate acids perspective, where we have the conjugate acid is forming the base and the hydrogen ion. Because we can do a very similar thing to before. If we think about our Ka for this, it's going to be our products, which is our base times our hydrogen ion concentration, divided by our reactants, which is our weak acid there, which is our conjugate acid there. So if we know the concentration of that and that, which we would in our buffer solution, and if we're given a Ka, we can do the same thing. We can rearrange for hydrogen ion concentration, and then we can plug that in the pH equation. So our Ka expression there would be that one that I just did. So look, here's one if you want to have a go at applying that and see what you come up with. Calculate the pH of a buffer solution consisting of 0.2 mole per decimeter cubed ammonia, 0.1 mole per decimeter cubed ammonium, if the Ka value of ammonium is that. And we'll go through that answer over here as well. So let's consider this. So like I say, we've got a base accepting a proton to form the conjugate acid, NH4 plus. Well, let's consider that from the NH4 plus perspective. NH4 plus is going to go to NH3 plus hydrogen ions. So if we were to write a Ka for this expression, Ka is equal to the ammonia times by the hydrogen ion concentration divided by the ammonium concentration. Now, in our question, we were given that, and that, so we've got to rearrange to make hydrogen ion concentration the subject. So let's go ahead and do that. If we bring the NH4 over, we're going to have Ka times by NH4 plus is equal to NH3 times H plus. And then we've just got to bring the NH3 over. So that'll give us the concentration of our hydrogen ion is equal to our Ka times by the conjugate acid divided by the weak base concentrations that we were given in our question. So if we go ahead and if we plug all that in, what were we given? We're given a Ka of 5.8 times 10 to the minus 10. And then we were given ammonium concentration of 0.1 and ammonia of 0.2. So that'll be 0.1 divided by 0.2. If we plug this in, we're going to end up with our hydrogen ion concentration, 5.8 times 10 to the minus 10, times by 0.1 divided by 0.2. That'll give us an answer of 2.9 times 10 to the minus 10 moles per decimeter cubed, which we go ahead, we plug this in our pH equation. pH is equal to minus log times by the hydrogen ion concentration. We have an answer for that above, minus log of 2.9 times 10 to the minus 10. This will give us an answer in that alkali region, in that basic region, which is 9.5 to two significant figures there as we were given in our question for our values. So coming over here, and we end up with a pH of 9.5. Fantastic. So some calculations there. Let's just finish up with a bit of a discussion about some of the applications of the buffers, and one in particular in biochemical systems, organisms such as humans, because they play a very important role, as we'll see. So what have we got here? Many processes require maintaining a stable pH. Fermenting alcohol, electroplating, various manufacturing for dyes, cosmetics, for printing. But importantly for us, we're going to talk about this biochemical application. Many animals require constant pH levels. Humans in particular require an average blood pH of about 7.4, where it can vary between 7.35 to 7.45. Now, it's very important to keep our blood pH within these regions, because if it goes too far in the acidic or the basic directions, it can be pretty nasty. It can certainly be fatal. Blood that is too acidic or too alkali leads to conditions called acidosis or alkalosis. Obviously acidosis for acidic, alkalosis for alkali/basic, and these can be fatal. So there needs to be evolutionary mechanisms that we've evolved to be able to maintain a constant pH. And we've got all sorts of buffers in our body. A number of different buffers, such as hemoglobin, a bunch of phosphate derivatives, H2PO4-, HPO42-, bone, apparently is a buffer, and hydrogen carbonate, which is the one we're going to look at how it works. Hydrogen carbonate. All right, so cellular respiration, the reactions that give us all our energy, that classic reaction for respiration where you got sugars, C6H12O6, reacting with that delicious oxygen we're breathing in, forming carbon dioxide and water as byproducts. Our balanced chemical equation there, I'm sure you're familiar with that in some form. So look, we're generating carbon dioxide and water as byproducts of this cellular respiration, in addition to the energy that we get in order to do all those bodily things we have to do. We release this carbon dioxide through ventilation by exhaling. That's how it gets out of our body. But what can happen, or what does happen more, H2O and CO2 form mildly acidic carbonic acid. So we have the CO2 and the H2O can exist as an equilibrium with this carbonic acid here. Now this carbonic acid itself is a weak acid, so this has a equilibrium between hydrogen ions and carbonate ions. Or better yet, let's write it like this, bicarbonate ions, hydrogen carbonate ions, because that's what we're looking at more accurately. So we can simplify this process just as that. H2O and CO2 form the mildly acidic carbonic acid that can dissociate into hydrogen ions. So to write that just in one step, I've got that like this. And what you can see here is we've got H+, and if we're thinking about H+, we're thinking about acids and bases. What would happen if the blood gets too acidic? So we can think about how this hydrogen carbonate is buffering the pH of the blood. Well, talking in that Le Chatelier's principle once again, blood gets too acidic, it's going to increase the concentration of hydrogen ions, and we're going to shift that equilibrium to the left. That's going to decrease the concentration of hydrogen ion, and we're going to maintain that blood pH. What about if our blood gets too alkali? Well, the opposite. It's going to decrease the H+. As we've been saying, too alkali, adding OH-, they can react, the H+ decreases, but this equilibrium can shift to the right-hand side, and what that does is that's going to increase the hydrogen ion concentration once again, and we're going to maintain the pH, acting as a buffer there. Fantastic. Final thing is our carbon dioxide is also in this equilibrium, so its concentration is also going to affect blood pH. So we say that we release carbon dioxide through ventilation, but if the ventilation isn't occurring the normal amounts, you think about it's happening too quickly, too rapidly, hyperventilation, certain conditions can bring that on, or hypoventilation, where you're breathing much slower and you're not expelling as much as you should, as opposed to expelling too much in the case of hyperventilation, Hypoventilation, also conditions will bring that on. So this is also going to affect blood pH. So let's consider both of these examples. Hyperventilation, where you're overbreathing. So that means that you're expelling lots and lots of carbon dioxide. So the concentration of carbon dioxide is decreasing more than normal, eliminating more carbon dioxide more than usual. So what's going to happen is the equilibrium shifts to the left-hand side and we decrease the amount of H+, which makes it a more basic blood pH. The blood pH rises into that basic region, and that's going to have certain physiological effects that occur. Similarly, but the converse is the hypoventilation, is underbreathing, where you're not expelling enough carbon dioxide, so the carbon dioxide is building up, the concentration is increasing. So that's going to push the equilibrium to the right-hand side. Equilibrium shifts to the right, so that means our H+ is going to increase in concentration. It's going to become more acidic, so the blood pH lowers. So that's where we can have the things that we talked about over here, where if that blood pH differs too much, then there can be some negative health consequences. Fantastic, and on that cheery note, let's finish up the lesson here. What do? We have defined a buffer solution. We explained how a buffer solution can be made. We explained how buffer solutions control pH using some chemical equations. And right at the end, we described and explained the use of buffer solutions, including the role of hydrogen carbonate in controlling pH in blood. We calculated the pH of buffer solutions given appropriate data as well. Brilliant. As always, some tasks. If you want some consolidation, pause there, 1 column at a time from the bottom to the top, and that'll help you along. Brilliant. Thanks as always. I look forward to the next one as we continue on looking deeper into Equilibria. Have a good day. See you then.